Hi everybody. Today I'm going to continue our discussion about projectile motion and the trajectories that they follow. And I want you to learn this skill as we go through this. And that is to take two-dimensional motion and really break it back down into its one-dimensional components. So we've worked on that a little bit with vector addition, but I want to reinforce it today with the motion of a projectile and how it really can be thought of as all horizontal motion and all vertical motion that somehow come together to form the parabolic trajectory that it follows. So I'm going to ask you to kind of bear that in mind, that you're really thinking about two separate problems that are related, but they are separate. And so we're going to try to go through that today. I'm also going to ask you to remember that we're using ideal projectiles, which means no air resistance here. If you have air resistance, it's going to change the shape of the path, the trajectory that a projectile follows. So it's going to change it usually on the back end here. So you'll see as our projectile gets launched, it would actually be launched to a lower height, and then it would not make it as far because air resistance would slow it down. We're not worried about that for this. So we're just learning the ideal projectile trajectory skills. So that's what our goal is for today. Okay, so I've drawn out, as you can see, roughly a parabolic trajectory for a ideal projectile. And so I want you to think about it like this. So initially, this object is given a velocity that looks something like that. So this would be its launch velocity or initial velocity. I'm just going to put a 1 there. I might sometime later put an ln for launch velocity, but I just want you to keep in mind that that's the initial velocity right now. Now notice I have these numbers inside of each of the spheres that are being launched, the projectiles that are being launched. So those represent the times. So this is 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and 6 seconds. So at 0 seconds, it has this initial launch velocity, and it's a vector, of course. And what you see as you look at it is because it's at an angle, it has some horizontal and some vertical. And so we want to try to analyze things as best we can with that in mind. And so I'm going to try to draw out here what that would look like. But to do it, I want to just point out a couple of things that you may not have noticed about projectiles. First, let's look at only the horizontal. We did an entire video analysis about this where you learned this for yourself. And that is that the position of the horizontal position, of a projectile, it has an interesting feature. And that is, as it goes across its path, you may notice, and I tried to do the best I could with this, but it's not going to be perfect. You may notice that its position changes by the same amount for a unit of time. And so, and I mean horizontally, of course. So this is its x sub 0 position, 0 meaning at time equals 0. So this is its x sub 1 position, this is its x sub 2 position, and so on down the line. So if I ask you what was its horizontal displacement for each second, you should be able to draw out the vector that looks like this. And that's its horizontal displacement. And I think you will realize as you go through here, I tried as hard as I could to show you that the horizontal displacement at every single time is the same. The only thing that would change that would be air resistance, but we kind of ignored air resistance for this. Why is that the case? Well, what forces are acting on the projectile horizontally as it moves through the air? If you neglect air resistance, there's really nothing. So I'm again assuming you're talking about the moments after the launching force has been applied. So we're not even considering the launching force. That's over already. The object has this velocity, and so therefore it's now moving both horizontally and vertically because of that initial launching force. But that's over. And so there's no force that's acting horizontally on it. And so if I ask you what was its displacement every second, you could show me horizontally its displacement looks like this every second. And wouldn't you agree those are roughly the same for every single second? Now, you might remember that the velocity of an object is equal to its displacement. Oops, excuse me, sorry about that. And by displacement, I mean its change in position vector divided by the amount of time that it takes to change. And so you see, this is the amount of change in the position in every second. So this is basically equivalent to the velocity vector. The displacement per second is the velocity vector. And I think you'd agree that the horizontal velocity, I'm going to put a sub h there, is constant as it goes across its path. That makes things easy, right? So the horizontal velocity looks like that little vector right there. Now what about the vertical velocity? Wouldn't you agree that the vertical velocity is being altered because of the force of gravitation, right? So initially, the vertical position is here, and then the vertical position is here, and then it's there, and then it's there, and then it comes back again, and then it comes back again, and then it comes back again. And so it starts off here, goes up, and then comes back down again. Vertically, you can see that we have some positions that are related as we go across. So this is your, say, y sub 0, and this is your y sub 6. This is your y sub 1, and this is your y sub 5. This is your y sub 2. This is your y sub 4, and this is your y sub 3. And so I think you'd see that the change in the vertical displacement, so the vertical displacement in 1 second, excuse me, that should be a y, looks like this. So from 0 to 1 looks like that. And then for the next second, looks like this, from 1 to 2. And then the next second looks like this, from 2 to 3. And then it reverses itself as it goes back down. And so I think you'd see that the displacement, the size of the displacement vectors gets smaller and smaller as it goes up to the top, and then gets larger and larger as it comes back down again. So each of those displacement vectors is the amount of displacement in 1 second. As we noticed here, the amount of displacement in 1 second is the velocity. And so if I wanted to, I could say this was actually the equivalent to the vertical velocity in the initial state right there. And then this is now the new vertical velocity. And then this is now the new vertical velocity. And so I think you'd see that it's changing. How much is it changing? Why is it changing? It's changing because there's this thing called the acceleration due to gravity. And so the acceleration due to gravity always acts downward. That's little g. And it always acts with a strength of 9.81 meters per second per second. So every second, the vertical velocity is changing in the downward direction by 9.81 meters per second. So what you're seeing here is that it's slowing down, slowing down, slowing down, stopping right at the top, and then speeding up, speeding up, speeding up as it's going. But every single second, it's still changing by the same amount in the negative direction. Hopefully that makes sense. So can we say we have our horizontal velocity is constant? That's easy enough. But our vertical velocity is not. And so that's what gives it this parabolic shape, is that the vertical velocity is changing every second because of this gravitational acceleration. And remember that the acceleration vector, that's a vector right there, is the change in the velocity vector divided by the change in the time. Hopefully that makes sense. So if you think about it in that way, you could use this formula here. Change my color again here. Let's go purple, I think. Why not? There we go. So the horizontal velocity is a constant. Equals a constant. So if I wanted to figure out how far it moved, I could use this formula right there to be able to figure out what its horizontal displacement is at any particular time. No problems, right? What about the vertical velocity? Well, the vertical velocity is an interesting problem, and it's a problem that is very similar to ones that you had when you were in Unit 2 and you were just launching a ball straight up into the air, because that's basically what's happening in the vertical dimension right here. You're just launching the ball straight up into the air. And so if you want to figure out what the vertical velocity formula looks like for this, you're going to need to use something that has initial velocity and time and acceleration in it. And so, because the acceleration means that it's changing, right? So the vertical velocity formula for this is actually going to look like this. The initial velocity plus the acceleration velocity, or acceleration vector, excuse me, times t. So that's going to tell us this is going to be the velocity that it has in the vertical dimension at any particular time. So this is your instantaneous velocity. This is also your instantaneous velocity, but it's also the average too because it's a constant, so it doesn't really matter. That's why you can use this formula right there. So we can use this to try to figure out the vertical velocity and this to figure out the horizontal velocity. And then when we put those two vectors together, look what happens. So if I take the horizontal vector, so v sub h, which you got from here, and the vertical velocity vector, which you got from here, you can use the parallelogram method or any method that you like to go ahead and add those vectors, and you can figure out what the actual velocity of the object is. The projectile's actual velocity is found by using those two, that vector addition, where you have a horizontal component and a vertical component added together. Hopefully that makes sense. Now, one last thing, notice that you have symmetry, okay? So if I wanted to, I could divide this situation into halves right here, right? So I have an initial state where I have an initial velocity that's both horizontal and vertical, and then it goes up to a place at 3 seconds where the velocity is only horizontal, right? Right at the top of the path, there's no vertical velocity, and so the velocity is only horizontal at this point. What that looks like is something like this, right? So you start off with a velocity like this, then you have a velocity like that, then you have a velocity like that, and then it's all horizontal. And then it begins to move back down again, like so, until finally you have a velocity here that looks something like, and I'm going to draw it over here so you can see it a little bit better, something like way down like that, which is the exact opposite of this. So one of the things that's interesting that you see here is that this velocity and that velocity are the same, just flipped over. This velocity and that velocity are the same, excuse me, this velocity and that velocity are the same except flipped over. These two velocities are the same except flipped over. This one is just by itself. And so what you notice is I drew this line right here, dividing this into an upward and downward phase. And the upward phase and downward phase are both symmetrical. And so there are many, many ways where you can use the idea that they are symmetrical for the way up as they are for the way down to be able to make your math a lot easier. And so we'll do some practice based on that. Hopefully that helps. If you have any questions, please let me know. We'll be doing some practice here in the next few days, so get ready for that. Take care.